Chapters 11 and 12, Estimation of Absolute and Relative Performance, Part 2. Let's have an example here. It's about a software made personal, SMP. So SMP receives calls from customers from 8 a.m. to 4 p.m. and customer will wait if the operator is not available. Okay, so we have modeled this system as a simulation model, and we have run it for 4 replications independently, and so we do have the average waiting time on each replication. And so now we want to construct a 95% confidence interval for the average color waiting time. Okay, so I see here we have the average waiting time for 4 replications. So based on the equations that we have, at first we can obtain the y bar dot dot. It will be the total average waiting time over the replications. So it's 2.64. So it's somehow, it's actually the point estimation of the average waiting time for a color. Okay, so that's the point estimation. So we want to have a confidence interval in order to know about the error. Okay, so to do so, at first we calculate the sample variance, and then by having the equations for the half width of the confidence interval, we can obtain the half width of the confidence interval, and then by having that, we can form our 95% confidence interval. Okay, so let's see here, it's this. So the half width of the confidence interval is 3.62. So the average, the y bar is 2.64. So 2.64 plus minus 3.62 will be our 95% confidence interval. Okay. So as we saw, the half width or the half length of the CI confidence interval is this. Okay, so yeah, here S is the sample standard deviation and R is the number of replications. So what question arises here, that how many replications should we have in our simulation? What's a good number for R? Okay, so we can actually estimate a good number of R on replications based on an error criterion, let's say epsilon. So this will be an allowable difference desired by the analyst. Okay, so here suppose that we have an initial sample size. Okay, so yeah, it could be any number greater than or equal to 2, for example 2 or 10 or more, better. Yeah, so we'll have an initial sample size, and based on that we have calculated the sample variance, and also we can calculate the half width of the confidence interval, right? So here we can set this should be less than or equal to the epsilon, the desired error level. Okay, then by solving that inequality for R, let's say R is unknown here, and then we can obtain the R as the smallest integer satisfying R be greater than or equal to R0. So if we have an R0, and let's say initial sample size, and then we solve that inequality, and if R is less than R0, so we are not going to decrease the number of replications, we will keep that R0. But if R is greater than R0, so we will increase the number of replications from R0 to R. Okay, so yeah, R will be obtained by this inequality, and we can actually change this equation or transform this equation for this in order to have an initial estimation for R. Okay, so here, as you see here, we have replaced the t distribution by z half alpha. Okay, and yes, and after that we can shape our uh, confidence interval as well. Okay. So let's have an example here for the SMP example. Suppose that the desired estimate for the mean waiting time is within plus minus 0.5 minutes with 95% confidence. Okay, so what should be the R then, the number of replications? So from the previous example, from 4 replications, as you remember, the S0 is calculated as 2.28. So the alpha here is 0.05. So by having the alpha that number, the Z, the standard normal distribution for 0.05 divided by 2, half of 0.05 will be 1.96 from the standard normal distribution table. Okay, so by having these numbers, then we can easily calculate the R by this inequality, and it should be greater than or equal to 79.88, which is 80. So here we'll conclude that the required number of replications in order to have the precision of plus minus 0.5 minutes is 80. Okay, so then the desired 95% confidence interval can be constructed by having the statistics obtained by the 80 replications, not with the 4 replications. So right now we do have 4 replications, so we need to run the simulation model for more 76 replications in order to have 80 replications in total, and then we need to recalculate y bar dot dot and s from the 80 replications data, and then based on that we can form our confidence interval, which will have the precision of plus minus 0.5 minutes. Okay. When we're using Arena, they are providing the confidence interval, and some other applications may provide minimum or maximum on the point estimator. So usually we do have y bar dot dot and h. So as you see here, this is a screenshot of the result obtained by the Arena, and we do have here the half width. Okay, so so by having a result of Arena, so how can we estimate the standard deviation? So here we can use the equation for the half width of confidence interval, and we can easily obtain S, I mean the estimation of standard deviation here by having the half width and the number of replications. So as you see here for this example, the number of applications is 5, and we do have half width, let's say for part A as 0.7. So the alpha in Arena is usually is 0.05. Yeah, by default it's with 95% confidence interval, or alpha is 0.05. So yeah, you can easily, by having these values, you can easily estimate the standard, I mean the sample standard deviation. Okay. Steady state simulations. In steady simulations, we have a single run or replication, but it goes for a very long period of time. So here, since it's running for a very long period of time, we assume that n approaches to infinity. So theta here will be estimated by this equation. Okay. So, but actually n is not infinite, because we need to terminate the simulation in sometimes TE obtained by the analyst. So at the end, we'll have n number of samples on hand, but we know that it will be a very large number. So, and theta is independent of initial conditions. Yes, it's long enough to eliminate the impact of initial conditions. And if you're dealing with time continuous performance parameter, then we need to have phi hat, and phi hat will be calculated by this equation. Okay. So the termination time TE here is a design factor and will be obtained by the analyst. So it's not inherently obtained by the nature of the problem, like the bank or restaurants, for example. So in order to obtain TE here, we need to consider some concerns here. The first one is bias. So if the T is not too long, then the results will be biased on the initial status. And if we increase TE to be long enough to eliminate the impact of initial status, then it will be less biased on the initial status. So this is one consideration here. And the other one could be desired point estimator precision. So yeah, we can we have learned that how we can obtain this by having a standard error and half of confidence interval. Okay, half width of confidence interval. And the third consideration here is computational and time constraint in executing the simulation model. Okay, so yeah, if we have just one replication and we do have discrete time output results, then we will have the data as y1, y2, y, and so on. But if we have R replications here, we can also have replications, right? So if we have R replications, these will be our data set here. Okay. There are several methods to reduce the bias of the point estimator on the initial conditions. The first one is intelligent initialization. So here we can set initial conditions instead of assuming that the system is empty at time 0. That's one thing. Or we can use the real data from the actual system. So for the initial status, so by having that, we can say that the initial status is so close to the steady state behavior. So somehow we are reducing the bias of the results on the initial status. Or we can use the simplified queuing model to estimate the steady state initial conditions. So these are in the category of intelligent initialization. And the other method is considering warm-up period. So here we assume that we run actually the simulation for a while, and then we discard all data observed and update up to that point, and then we'll use the data collected after that point. So as you see here, we have a warm-up period here up to T0. So we discard all the results up to this point, and after T0, actually the data are collected and the result will be calculated based on these data after T0. So this is called the warm-up period method actually. Okay. This is a simulation can also be replicated, so we can use the replication method here as well. So here we assume that we have R independent replications, and at each replication we do have n observations on the results. Okay, so here we assume that the first D observations are for the warm-up period, so we will eliminate the first D observations, and then we'll calculate our parameters after D observations. Okay, so as you see here, we have our replications. At each replication, we do have n observation, but the first D ones will be eliminated because it's about the warm-up period, and then we'll consider D plus 1 up to n data. Okay, and the y bar 1 dot for replication of 1 up to y bar r dot average on the replication of r can be calculated, and then we can calculate the total average at the end for over all replications by var bar dot. So yeah, here we do have the equations, And by having the D as warm-up period, we assume that the expected value of y bar dot dot nd will be equal to theta, which is an unbiased point estimator. Okay. So if n and d are sufficiently large numbers, then theta nd will be equal to theta. Okay, so because of that, for simplicity, we eliminate nd from our notations in order to have y bar r dot and y bar dot dot for just simplicity. Okay, so the standard error can be estimated by this equation, and same as before, and the standard error of y bar dot dot again can be calculated by this equation, and at the end we can construct our confidence interval with 1 minus alpha percent confidence level. Okay, let's have an example here. We have the simulation of fast chip wafer, and it's simulated for 10 replications and 2,200 hours, and the first 200 hours is warm-up period, and the observations for that warm-up period has been eliminated, and here we do have the average for the long run cycle time for 10 replications after eliminating the warm-up period data. Okay, so now we want to have a 95% confidence interval. Okay, so easily we can obtain the y bar dot dot here, and it will be 46.86, and then the standard error of y bar dot odd s over the square root of r will be 0.15, and this value will be obtained by the t distribution table by having the half alpha and a degree of freedom, which here is 10 minus 1, 9. Okay, so by having these values, we can easily construct our confidence interval with 95% confidence level. Okay, and here we have an initial replications, I mean 10 replications. We can serve this as initial replications, and if we have an epsilon, I mean a desirable precision level, then we can obtain the number of replications that we need to have in order to reach that precision level. Okay.